Okay, so I left you with this little problem to work out what temperature star would be needed in order to give majority of its photons at this sort of wavelength. So the magic 91.2 nanometers, which is the wavelength required, or you need to be shorter than this wavelength to ionize hydrogen. So again, applying what we've learned earlier in the course, then you can just use Wien's displacement law here to estimate when lambda max, the peak of the black body, will be at this wavelength. And if you do that, then you get about 33,000 Kelvin. Okay, so that's saying that you're going to need a star that's sort of this kind of temperature before it's going to pump out enough far ultraviolet radiation with a wavelength shorter than 91.2 nanometers that will ionize any hydrogen gas around it. So let's go back and look at a HR diagram again to see, here's the plot of temperature increasing to the left here, and luminosity going up this way. So what type of stars are over on the far left of this HR diagram that are hot enough to ionize hydrogen? Well, you can see that the massive main sequence stars up here at the top end, top left corner of the HR diagram are the only ones that are really going to fulfill this criteria. Okay. And they're also very luminous as well. So that means they're pumping out a lot of photons, and they're going to be hard UV photons that can ionize hydrogen. So we're sort of interested in the massive main sequence stars here. So this brings us to the topic of what we call H2 regions. So this is the way to read this title. So this is a Roman 2, so H2. We'll come on to some terminology in a moment. So it's as we've just seen, it's the massive main sequence stars that have these high temperatures. But it's no good having lots of photons, hard UV photons, far UV photons coming out of a star if there's not much gas around it to actually ionize. So to make these kind of regions of ionized hydrogen visible in the interstellar medium, you need actually quite a bit denser gas than the typical sort of interstellar medium density. Now, very young stars, so the young massive main sequence stars, will naturally be still surrounded by very dense gas, because the fact they're young means that they've only recently formed out of a cloud of interstellar gas. So in order to form a star, again, we'll come back to this a few times, you're going to need a cloud of gas, interstellar gas, that collapses under its own gravity to pull material in and to collapse right down to form a new star. But of course, as it does that, as soon as it forms, it's still going to be surrounded by a cloud of dense gas. So by dense here, we mean about something like 10 to the 10 per meter cube. So if you recall, the typical average interstellar medium density is 10 to the 6 per meter cube. So this is 10,000 times denser than the typical interstellar medium. So these numbers are just ballpark numbers, sort of order of magnitude numbers. But we're setting up the kind of conditions here. So these conditions will give rise to an ionized nebula. So again, nebula here means a region of extended sort of diffuse light in the sky, and these are referred to as H2 regions. So this terminology here, H2, we've kind of met it before, okay, when we were looking at spectra, spectroscopy. So this is spectroscopic notation again. When we originally looked at spectra, then we were talking about H1 lines being like atomic hydrogen, the Balmer sequence lines due to transitions within atomic hydrogen. So H2 is the ionized version of that. So H2 means ionized hydrogen, okay, or H plus would be the sort of physicist notation, if you like. Basically free protons and electrons. And not only does the radiation from these stars heat up ionize the hydrogen, it also heats it up. Okay, so a lot of the photons that ionize the hydrogen, that remove the electron from the ground state and put it into the, remove it from the atom altogether, they will have excess energy. Okay, so they'll be shorter wavelength than 91.2 nanometers. Any extra energy above that needed for ionizing the electron goes into kinetic energy of the electron, and that then basically turns into heat. So the gas is also hot. Okay. So the typical parameters for an H2 region are these sort of densities, 10 to the 10 per meter cubed and 10,000 Kelvin. So hot, dense-ish gas. And what we want to go on to now is how to observe this kind of gas. Well, basically, hot gas is the kind of thing that you have in a typical sort of fluorescent tube, possibly above your head right now. And so hot gas tends to fluoresce, which is the process by which hot gases emit radiation, in particular in the optical spectrum. So let's see a picture of one. This is a very famous H2 region, the most famous H2 region, really. This is a region that was referred to as the Orion Nebula. So this nebula, again, you can almost see it with the naked eye. It's in the sort of, if those of you familiar with constellations, it's in the sort of sword of Orion, below Orion's belt. There's a little misty patch, easily seen with binoculars or a small telescope. So you see this is a picture from the Hubble Space Telescope, so it certainly doesn't look like this with a small telescope. But you basically see a sort of glowing misty patch. Okay. So this is what we mean. All of this light here is due to the gas that's fluorescing away. And in the Orion Nebula, you can actually see the stars in the middle here that are providing all of that energy to heat up and ionize that gas. There are actually 4 of them. The brightest one is here. So there's 4 stars here, referred to as the trapezium. So those 4 stars are all hotter than 30,000 kelvins. I think this one's up at about 40,000 Kelvin. So they're pumping out the radiation that's ionizing all the gas here. And you can see probably there's a lot of material around. We're going to go on to talk about dust clouds. You can see that there are basically just clouds of gas and dust around here. Okay, so how is this gas emitting? Well, it's basically emitting through having an emission line spectrum. So this is the kind of opposite to how how stellar spectra look, which have absorption lines. Here we're now talking about emission lines. And the conditions you need to form an emission line spectrum are basically the opposite of what you need to form an absorption line spectrum. So now we're talking about viewing a body of hot gas that is viewed against a background of colder material. Okay? And in this case, we're really viewing, like in the case of the Orion Nebula here, you're just viewing it against the cold background of space, really. Okay. So as long as we've got hot gas, well, any kind of gas really will, if it's sort of lowish density, will give you an emission line spectrum if you're viewing it just against the background of cold space. So let me bring up this diagram that we had once before. Okay, so before we were talking about absorption lines. So the idea in stars where you've got cooler gas in the atmosphere against the hotter interior of the star, that gives you an absorption line. Now we're sort of viewing along this angle, so there's no background here now from this line of sight, but we've got this cloud of gas. Even though it says cooler here, it's still hotter than the background of cold space. Okay, so that will give us an emission line spectrum. And if you've ever sort of had a demo or been in the lab where, again, you look at a sort of fluorescent tube with a prism or a spectrometer, then you get an emission line spectrum. It's exactly what happens in sort of street lights, where you heat up gas with an electrical current, and it basically fluoresces. Often the sort of sodium lights, which are full of sodium vapor, heated up, and that gives rise to that sort of orange glow. Same principle. Okay, so if you look at if you take a spectrum of one of these nebulae, like the Orion Nebula, you see that basically there's no continuum at all. It doesn't look anything like a black body. So that's an important lesson here. Not everything out there emitting in space or anywhere else for that matter emits like a black body. You know, usually only quite sort of dense gas would give you a black body, like the dense atmosphere of a star. When you've got this low density, tenuous hot gas, then you tend to get an emission line spectrum. Now, as we said already, the composition of this gas, this material in the interstellar medium, it's the same as it is in the stars, because the stars are made out of this stuff in the first place. So again, this is 75% hydrogen by mass. And it turns out that the strongest line here is actually usually the H-alpha line, but this time in emission, not in absorption. And how is the H-alpha line formed in these circumstances? Well, it's a bit different this time. So here you've got a gas that's mostly ionized, so it's free electrons and protons all moving around. But even in those conditions, every now and again, the electron will come along and recombine with a proton to form a hydrogen atom again. And as the electron cascades down through the energy levels in the hydrogen atom, going down towards the ground state, it will emit photons as it's going. And if it drops from n equals 3 down to n equals 2, then it will emit the H-alpha line. Okay. So this is now the H-alpha line in emission. So I've written a little equation here at the bottom to illustrate this idea that, in a sense, there's a dynamic equilibrium going on in these H2 regions. So you've got this, it's not a chemical equation, but it's a physical process equation, if you like. So you've got photons, as illustrated by a packet of energy here with Planck's constant h times nu, which is the energy, nu is the frequency. And that energy is interacting with so it's a photon interacting with a hydrogen atom, and that will ionize it to give a proton and an electron. But as I've just said here, then this process can go the other way. The electron can come along, combine with a proton, and give us back the hydrogen atom again, all the while emitting photons of discrete wavelengths corresponding to lines in the hydrogen spectrum. So here's an example of a spectrum from an H2 region. So this is an optical spectrum. Excuse the scale. Sorry, this is in angstroms again, sort of, but just divide by 10 to give wavelength in nanometers. So this is 400 nanometers, and this is 650 nanometers. So here's our H-alpha line again, just at the red end of the optical spectrum. Okay, and you can see the other Balmer lines. There's H beta and H gamma here as well. Get the whole series, and some other elements also producing lines, but let's not worry about that. We've got some helium here as well. But you can see by far the strongest line is the H-alpha line, which is at that red end of the spectrum. So you may recall that earlier I was talking about those sort of glowing red patches of light in the spiral galaxy image that I showed you. So that they are basically picking up the glowing regions of H-alpha from these H2 regions. And so that's why I said that those glowing red patches are due to hot gas, basically H2 regions. And you can see that they're all in the spiral arms. Okay. And that, as we shall see later, you know, the spiral arms are basically where all the massive stars live in a spiral galaxy. That's where the young blue hot stars are that trace out those spiral lines. Okay, so H-alpha emission is one good way of studying H2 regions, but they also emit very strongly in the radio. Okay, and this is again something that's close to my heart. So I've been studying H2 regions in the radio for a long time now, how does this occur? Well, Recall that we've got these free electrons that are moving around in basically a sea of ions, basically protons, positively charged protons. So, what's going to happen when a negatively charged electron comes along and interacts with a positively charged proton? Okay, there's going to be an electrostatic attraction between them, and the electron, which is much lower mass, of course, will get accelerated by the ion. And an accelerating charge always emits electromagnetic radiation. Okay, so if you accelerate any charged particle, it will emit some kind of electromagnetic continuum radiation. And depending on the sort of energy of that interaction, determines the wavelength, if you like, of the emitted radiation. So this process you may well have come across before in physics. It's referred to often by the German term Bremsstrahlung, which stands for breaking radiation. Okay, so this was the type of radiation that was initially used to detect X-rays for the first time. But of course, that's a more energetic process where you fire electrons down a very high speed sort of electron gun and smash them into some sort of heavy material like lead or whatever to slow the electrons down very rapidly, and that gives rise to high energy electromagnetic radiation in the form of X-rays. Here you've got much slower moving electrons. They're just moving around with whatever the temperature of the gas is, in this case 10,000 Kelvin. This is why I refer to this process as a thermal Bremsstrahlung. Okay, so that the particles, the electrons and the ions are moving around just with their normal thermal gas speed that they would normally be doing. Nothing weird going on. So that's the kind of process, and that gives rise, in this case, to emission at radio wavelengths, so a continuum emission at radio wavelengths. And in particular, around about wavelengths of around about 1 centimeter, okay, so something you can easily visualize, is the kind of wavelength where this process emits very strong radiation. So here's just a little graphic to illustrate that Bremsstrahlung process. So here is the path of the electron. It's coming along, starts to feel the electrostatic attraction of the positive nucleus of the negative electron, and it just swings around and gets accelerated as it goes. And depending on the kind of radius of curvature here, it determines the wavelength of the emitted photon. So you can see that there's going to be a range of wavelengths emitted. You've got a range of speeds, you've got a range of distances. So that gives a whole continuum of radiation. So it's not a spectral line. So again, please try and get those kind of things clear in your head. When is an emission process between two particular levels that gives rise to a particular wavelength spectral line? And when is it a range of wavelengths, range of energies that gives rise to a sort of continuum spectrum? Okay. So we can use telescopes that are sensitive to radio waves to make images. This is using the Very Large Array in New Mexico. So again, a telescope that I've used many times myself. In fact, I've made a survey of the entire Milky Way to find all of these H2 regions that we can possibly find throughout the Milky Way. But here you've got a nice comparison picture of the optical picture of the Orion Nebula that I showed you earlier, and now a radio picture of the same region, pretty much. Slightly different scale, but you can see the same structures. Okay, you can see the sharp edge here. So this is where the ionized bubble of gas runs out, and beyond this, there is no ionized gas. Inside, it's all ionized. Okay, so that's as far as the radiation extends, if you like, from the stars in terms of its ionizing effect. So you have this great big bubble of ionized gas here, and this would be the H2 region. The colors here are just false, they just represent intensity in this case. Okay. But you can see the same structures in both. Now, one thing that is different is that here, and we'll come back to this later, we've got what I will call a dust cloud. It's obscuring the nebula that's actually behind here, but radio waves are rather good at penetrating through all of that, and so here you get no obscuration at all. You can see everything. So that's a great advantage of radio astronomy, not affected by those dark lanes. Okay, so that was H2 regions, and we'll come back to them a few times, and their association with young massive stars and the formation of such stars. But now I want to keep moving on to the next phase of the interstellar medium. So we've talked about ionized hydrogen. Now I want to talk about atomic hydrogen and atomic gas in general, but let's keep it simple and talk about hydrogen. And here is where most of the mass of all of this interstellar gas in galaxies like our own resides. So most hydrogen out there that's in between the stars is in atomic form. And again, to keep this notation going, we'll see this time and time again, this is referred to as H1, so that's a Roman 1. Okay? So this is neutral hydrogen or atomic hydrogen. So, as I mentioned at the beginning of the lecture, then the typical density of the whole interstellar medium is about 10 to the 6 particles per meter cubed. And so this is true of the atomic gas because that makes up the vast mass of interstellar gas. So what kind of state is this gas in? So we're now, the H2 regions were in a special location because they had, as you've just seen, they had to be close to a hot star in order to feel the effects of that ionizing radiation from the hot star. But once you get a long way away from any star, you're a parsec away or so in between the stars, you haven't got any of that ionizing or heating effect. The radiation is not strong enough. Okay, so the general radiation of background starlight is not very intense in interstellar space. So therefore, there's not very much in the way of heating of the gas, and so therefore it is much cooler. So a typical temperature for this interstellar atomic hydrogen gas is around about 100 Kelvin. Okay. And as we shall see in a moment, if hydrogen gas is only at 100 Kelvin, this is very different to the conditions in sort of stars where you've got many thousands of Kelvin and the hydrogen gas can be excited, and so that's why we see things like the Balmer series lines, etc. Here we're much too cool for that, and so all the hydrogen atoms the electrons are basically stuck right down in the ground state in terms of the energy level diagram. So they can't go up to n equals 2 and back again, and let alone any further up. So how are we going to observe this gas? Well, basically there's no kind of transition that we're going to see sort of in the optical spectrum or anything like that, which makes it a bit tricky. But luckily we are saved, again, by another aspect of quantum physics, and that's because there are other types of energy levels and transitions within the hydrogen atom. So rather than just the sort of electron orbiting the proton, giving rise to the sort of typical n equals 1, 2, and 3, what are referred to as electronic transitions or energy levels, there are other energy levels as well. And the ground state of hydrogen is actually 2 separate levels, as I'll show you in a moment, and you can have transitions between them. And these are referred to as hyperfine transitions. Again, don't get too hung up on the terminology here. The key thing here is that transitions between these 2 levels occur at a wavelength, a very special wavelength in astronomy of 21 centimeters. So this is very much in the radio part of the spectrum as well. Okay. So what's going on? Why do we have this? Why do we have these energy level transitions? Well, it's all to do with the spin of the electron and the proton in the hydrogen atom, rather than the sort of orbit of the electron. Okay. So a fundamental aspect of quantum physics, as I'm sure you've picked up in the past, is the idea that any type of angular momentum is quantized. Okay. So those normal energy levels in a hydrogen atom are due to the fact that the orbital angular momentum of the electron orbiting around the proton, that is quantized. But here, as well as orbiting around the proton, the electron also has its own spin. Okay, so the electron spins, and so it has some spin angular momentum as well. And so does the proton in the nucleus. Okay, it also has spin. Okay. And again, quantum rules basically dictate that there's only two states that these sort of spin vectors or spin angular momentum vectors can orientate themselves. They can either be parallel, like in this case, or antiparallel, like in this case. So that's another quantum rule. You'll see in physics the idea of spin up and spin down. And so that's the idea here. So these are the two states that define these two energy levels. And this state, where the spins are antiparallel, is a slightly lower energy state than this one. And the difference in energy between them will give rise to this 21 centimeter transition. So the way this works, well, let me go to a little energy level diagram here. So this is our previous energy level diagram that we had before. So these n equals 1, 2, 3, these are what quantized states of orbital angular momentum for the electron. But here, if you zoom in like a millionfold, and you can see the scale here, right? This was tens of electron volts. So this is a massive, this is why it's called hyperfine. This is a very fine splitting of the ground state. So all the electrons in this cold interstellar gas will be here in the ground state. But if you zoom right in and look at the very fine quantum levels, you find that there are actually two different levels here, and they're split by a very small amount of energy. So again, most of the time the electron would be in the bottom one of these, but it doesn't take much energy to flip it into the next level up. And so that's in interstellar space, that's actually done by collisions between hydrogen atoms. So two hydrogen atoms will collide together, and it's enough to give that electron a little bit of energy and pop it into the higher state. Then sometime later, the electron will relax back down to the lower level, and as it does so, it will emit a photon corresponding to that energy gap, which is 21 centimeters. Okay. So just going back to the spin flipping thing. Most of the time in this level, a collision will come along and flip the electron into this state, and then sometime later it'll flip back again. And during that transition is when we get the photon at 21 centimeters. So that gives rise, this is a spectral line again, right? You've got well-defined energy levels and a transition between them with a very specific wavelength. So this is going to give rise to an emission line. Again, as long as you've got your 100K hydrogen gas in front of, it's never quite zero in space. You've always got the 3K microwave background, of course, but essentially zero. So the 100K gas is hotter than the background of space, because these clouds are very extended objects across the whole galaxy. And so you will give rise to an emission line. So here's an example. Okay, don't worry about all the blurb on here, and it's been put into a velocity scale, so the Doppler effect has been used to translate frequency or wavelength into velocity here, as is often done. But the idea here is you can see an emission line. Okay? And this is when a radio telescope has been pointed at an entire spiral galaxy. So you've got a whole spiral galaxy, like the one behind me here. You point your radio telescope at such a galaxy and record around a wavelength of 21 centimeters, and this is what you see. So you see all the hydrogen gas in that galaxy emitting due to this hyperfine transition. Okay, so this is the H1 21 centimeter emission line. And this is the way that we can map out atomic hydrogen gas in the universe. So it's a very powerful tool. Okay, so time for a break, and I want you to have a sort of go back and have a look at this spectrum again. So you can see that it's not just a simple sort of single peaked line. Okay, so you've got two components, if you like, one at a higher velocity, one at a lower velocity. Okay, and And again, you can just about see the velocity scale on here. So the central velocity here is about 1,500 kilometers per second. Okay. So the fact that we're looking at a spiral galaxy, have a little think about this. Okay, so why does it have two components? What is the velocity split between them tell us? So what's this velocity difference telling us? And what does this central velocity here, the velocity of the average velocity of the entire line, tell us about this galaxy? Okay, so have a think about that, and we'll come back after the break.